Okay, Amanda, so we're ready. We're ready to start. Okay, so since I don't hear any objections to starting, I'm going to start off. We're going to introduce Jed Pixley from Rutgers, who's today's colloquium speaker. As many of you know, Jed did his PhD at Rice with Chi-Miao Shi, a postdoc at University of Maryland with Shankar Dasharma. And he's been at Rutgers, my colleague in the physics department and in the condensed matter theory group since 2017. And we're really thrilled to have him on board. He's already acquired a whole, bunch of prizes and recognitions, including the Mott Prize from SECS, a Sloan Fellowship, the NSF Career Award, and AFOSR Young Investigator. He's been coming to Aspen for quite a few years. In the pre-family state, he was doing hikes and enjoying all the beauties of Aspen, just like as many of us know. Now that he has young kids, he's a little bit constrained in the rigor of the hikes that he can do. But as soon as youngest kid can make it to Cathedral Lake, they're going to be off and having a great time. So
hopefully.
Very good. Okay, so without further ado, here is Jed. So.
Thank you very much for that nice introduction, Karen. All right. Get mic'd up. I think so. Yeah, I'm good. Okay. Find a laser pointer that works. All right. Well, hello, everyone. Thank you for coming. This is the first talk I've given in a year and a half in person. So it's really a pleasure to see actual people in the audience as opposed to my own screen talking to myself. So today I'm going to tell you about a rather fascinating quantum phase transition in open quantum systems that's induced by applying local measurement rates. And this is something we've been working on for about three and a half years now. And I'm really excited to tell you the progress we've made. So before I get going, let me just start by thanking, let's see how I change slides. Okay, my collaborators. So a lot of the work in my group was done by my graduate student, Aidan Zabalo, as well as my postdoc, Justin Wilson, who's now starting his own group at LSU in the fall. And then our close proximity with Princeton and CUNY, we had a very nice collaboration with Sarang Gallapur-Krishnan, Michael Golans when he was at Princeton, and with David Hughes. And the second part of our work, when we really started to dive into trying to understand these logarithmic conformal field theories at this transition, which I'll tell you a lot about, we started talking to experts in these log CFTs, Andreas Ludwig and Roman Vasseur, and this led to a very fruitful collaboration, which we put on the archive maybe a couple weeks ago. Okay, so where we're going today, let's see what's going on. I see. Hopefully that works every time. So where we're going today, so I'm going to give you some overall motivation, general motivation to the quantum many-body problem and how we like to think about this and how this has motivated a number of different quantum simulators, both analog and attempts to build quantum computers. And that'll then bring us into the notion of entanglement transitions, that is transitions in the structure of the entanglement entropy. And I'll then talk about how we can study these transitions directly using hybrid quantum circuits. These are models that have measurements and unitary operations. And I'll describe certain limiting cases where we understand this problem quite well. And this maps to a percolation-like transition in space-time. In the last part of the talk, I'll talk about my group's contribution to this work, where we developed new methods to actually accurately locate this critical point and then characterizing the log CFT using a random transfer matrix description of the problem. Okay. So as a condensed matter theorist or condensed matter physicist in general, our goal is really to describe a large number of interacting quantum mechanical particles. So we're thinking about, say, a box of atoms or electrons that are described for simplicity for now by a time-independent Hamiltonian operator H. And if we want to know the dynamics of this system, starting from some initial state psi naught, it's just good old unitary time evolution of the Hamiltonian on the state producing the time-dependent wave function. Okay, and in condensed matter systems, we now know that putting together a large number of particles, you can get a fascinating emergent phenomenon that has kept a number of us busy for a number of years. And so in other words, there's a couple pillars of our field that represent unique emergent states of matter that we've been studying in great detail. For example, the notion of a superfluid transition. So here I'm showing you a direct image of a cloud of atoms of rubidium-87. So this is high temperature. This is a Maxwellian distribution of velocities, a broad Gaussian distribution of atoms. Upon lowering the temperature, a superfluid transition was observed in this ultra cold atomic gas that was laser trapped and cooled of neutral atoms. Another pillar would be superconductivity, moreover high temperature superconductivity that allows you to do this tabletop experiment in front of your classroom, which is what I also do in my many body physics class. So this is a high temperature superconductor that's been cooled with liquid nitrogen below its transition temperature. And due to the Meissner effect, it's levitating above a strong magnet. Another pillar, which has brought a lot of us together, actually all three of these topics has brought us together here in Aspen, which would be topological phases. And this is, I'm showing just a 2D electron gas in a perpendicular magnetic field, which gives rise to these quantized Hall plateaus in the Hall conductance, which is a topological phenomenon, which is why it's quantized. Okay, so we have a pretty good understanding of this phenomenon, but in general, the solution of the Hamiltonian that describes these systems is highly non-trivial. Okay, and so while we've been able to develop numerous methods and techniques to try to solve these, when we're encountering new problems, we're always faced with new methods and new attempts to solve them. So there's a completely different perspective on solving the many-body Hamiltonian, which would be to let nature do it. So what if we could build a machine or a system which emulates the Hamiltonian we want to solve, and we then just let nature run and do its course, which would then solve the Hamiltonian for us. We even actually heard discussions like this morning from David Goldhaber-Gordon's group, who's trying to emulate, for example, the Kondo lattice. So this was actually Feynman's, sorry about that, Feynman's vision. And this quote always stuck with me, so I just wanted to share it with everybody. I'm not going to read it, but I recommend you do. And so Feynman attended this first conference on physics and computation, and it was actually said that just him showing up to the conference gave the field a significant amount of weight. And now, you know, physics and computation is a thriving field, and quantum computing is really taking off. And he also said he had no idea how to give a keynote lecture, and he then gave a groundbreaking keynote lecture. And one of the first things he pointed out, and this always stuck with me, is nature is not classical. And in my work, I do a lot of simulations on classical computers of quantum many-body systems. And so this always stuck with me. If I could actually do this on a quantum machine, it would be much better. And so just to rephrase his quote in a simpler way, so if I could build a machine that realizes the many-body Hamiltonian I want to solve, and I let it run, I should just get the time-dependent wave function I'm interested in. And I can then compute properties of it by measuring properties of that system. So there are now, I would say, a number of examples that realize Feynman's dream. These are a number of cold atom systems or trapped ions, superconducting qubits, so on and so forth. And these can be designed with great accuracy to realize the many-body Hamiltonian of interest, and then they can be run to understand either physics we maybe already understand, but we want to think about it in a different way, or uncovering physics that we can never really uncover in a solid-state system. So let me just give you an example. So here I'm showing, again, this example of a superfluid transition, which I mentioned earlier. But of course, we knew about this transition many years ago in superfluid helium. Just an ode to our astro colleagues. This actually was not taken on Earth. It was actually taken in the space station. They were trying to get rid of Earth's magnetic field, rounding out the transition. But they didn't do a very good job, unfortunately. But it's a pretty impressive experiment nonetheless. So this is an example of phenomenon that we expected to see in this emulator, for example. So we kind of knew what to expect. But you also have situations where maybe you understand what you expect to see, but it's very hard to realize in solid state. For example, Anderson localization is very hard to see in solid state systems due to phonons and other effects, or the idea of many-body localization, which is close to impossible to realize in solid state, which is an example I'll present here. So I don't know why I can't change slides without clicking on it. All right. So the idea of a many-body localized phase is I have an interacting many-body Hamiltonian, and in the presence of strong disorder or strong quasi-periodicity, you can actually localize all of the many-body eigenstates. What I mean by that, I mean that these eigenstates have no level repulsion and the system actually remembers the initial state from which it came. It will never relax the thermal equilibrium. So in Emmanuel Bloch's group, they actually tested this idea using a 1D optical lattice. And so they constructed an emulator. It realizes an H in the many-body localized phase. And then they produced an initial state, which is very high temperature like. So they put an atom in every other site. Okay, so the charge distribution is very far from the ground state. And for a generic many-body Hamiltonian, if you run this time evolution, it should just relax to a uniform density state. So the imbalance of atoms on even and odd sites should go to 0. But if I'm in the many-body localized phase, I should remember the initial state from which I came. And as a result, I should never relax to the ground state, or never relax the thermal equilibrium. And so the experiment was done, and these, I mean, you know, the experiment is limited to some finite time scale, so beyond that, they can't say much. But what you see here is with no quasi-periodicity, this imbalance relaxes right away, and then turning on the quasi-periodicity in the presence of interactions, this imbalance does not go to 0, indicating the system has remembered the initial state from which it came, and it cannot relax to that thermal equilibrium. Okay, so the understanding of many-body localization, actually, a characterization of it, which I did not mention, is in terms of its entanglement entropy. And classifying many-body quantum states in terms of their entanglement was really, I would say, a necessity in quantum and understanding this quantum many-body localization phenomenon, because it's really a transition from a thermal state where you have a lot of entanglement to this many-body localized phase with a short range amount of entanglement. So let me just give you a little primer on entanglement. So as I just said, that we realized by studying these systems that another useful characterization of quantum many-body systems beyond simply correlation functions is actually the structure of the entanglement of that state, okay? And the transition I'm going to talk about later on is a very good example of this. And so let's just get warmed up. Let's take two spin halves. We put them in a singlet. So this is a superposition state. And now I want to compute the entanglement entropy of this state, okay? This is a notion from quantum information, but it's a quantitative measure. And so you can define this von Neumann entanglement entropy, which is nonlinear in the reduced density matrix after you've traced out this other region B, okay? So this is a very simple example. You can probably just do this in your head, tracing out region B. You arrive at a simple diagonal reduced density matrix, and you get a log2 amount of entanglement. So the local on-site Hilbert space is two states. This is the maximal amount of entanglement one could have from this state. And so we usually refer to this as one bit of entanglement. And often you can normalize things by this bit of entanglement. Let's align the spins or even anti-align them, but take them to not be in a superposition state. If they're no longer in a superposition, this reduced density matrix is trivial and the entanglement is strictly speaking 0, okay? So this is a very simple example. Let me zoom back out to the many-body problem. How do we think about this in the many-body problem? So let's imagine I have a bunch of spins and they're interacting with short-range interactions, and they realize basically like a, we call a resonating valence bond state or short-range collection of singlets. If I now trace out some subsystem, if it's a weakly entangled state, it's just going to count the number of bonds I cross, which is what the cut is doing. Each bond gives me something like a bit of entanglement, and it's just going to count the number of bonds I cut, which in this case will be the perimeter of that system. This is known as area law entanglement. So area law entanglement is actually incredibly useful notion to classify gapped Hamiltonians in 1D, because it actually was proven rigorously by Matt Hastings that if I have some energy spectra, this is a many-body energy spectra, here's my ground state with a finite excitation gap to the first excited state, any 1D Hamiltonian with this excitation gap is area law entangled, okay? So this is a notion of a weakly entangled state. But what if I took a state that was very highly excited, very high energy density state? More often than not, actually generically speaking, this is going to be highly entangled where you're cutting an extensive number of bonds in your cut. And so this is going to scale like the volume of the subsystem, which I cut the system. Okay, so many-body localization is an example where these highly excited states do not satisfy this. This would be area law in the many-body localized phase, just to connect to my previous discussion. But more relevant for this talk, would be taking a unentangled initial state, doesn't matter, just took a classical Neal state, and we time evolve this with some unitary evolution, producing a highly entangled, volume law entangled state, which would happen generically if H is some generic interacting many-body Hamiltonian.
Can I ask a question?
Sure.
So I don't know, maybe this is obvious, but why is it the high energy density states are more entangled? It seems I have some spin liquidy thing. I go to high temperatures, then I have, that looks much more like a product state with all these free spins. Paramagnetic.
So what? Oh, so the question was, why does a high energy density state reflective in large entanglement? And so I mean, a simpler example is usually just like free fermions. And you can think of the ground state as occupying your Fermi sea, just filling it up. But if you take a highly excited state of free fermions, you can put them in basically any occupation you want. And as a result, you usually will realize long range entanglement. So the spin liquid that you mentioned is just this ground state, right? So a highly excited state of a spin liquid, you'd have to act with a number of operators to produce some excited state up here.
Those are free spins at very high energies, right? So then
not necessarily, not a many body state at high energy density. No, that's different than a finite temperature. So finite temperature is going to smear over all states. I don't know if that's intuitively clear to you, but
yeah, I didn't get that. That's okay.
Okay.
There's a question from Matt Foster.
Oh.
It's not really a question, it's just a statement.
Oh.
Right, which is, how do you get hot hydrodynamic stuff from quantum matter? Well, it's somehow the information is non-locally entangled.
Yeah, so Matt's comment is information is non-locally entangled and the highly excited state is another argument for this. Thank you, Matt. Nobody can really hear you, so I'm going to repeat anything you say. All right. Okay, great. So yeah, but I mean, this was an example. This is, of course, a generic statement. There's, of course, situations where this is not true. But in our case, we're really thinking about this unitary evolution in long times. Okay, so to classify these states, we can kind of separate them into two. So we have weakly entangled area law states and highly entangled volume law states. And the other point that will be relevant to this talk is critical points. So in 1D, critical states acquire a log correction. So in between, so in D equal to 1, this is constant versus linear. And at the critical points in 1D, you get a log correction. This has been rigorously established using the power of conformal field theory via Calabrese and Carty. Okay, so this entanglement, while it's a useful way to characterize these quantum many-body systems, it's also a useful resource to do quantum computation. So you would need a highly entangled quantum computer to do anything beyond a classical computation. And as I'm sure many people in this room are aware, there's a worldwide race right now to build a quantum computer. And this is spurred both by the private sector. So this is just some of the sampling of companies I just found on the internet. And a number of these are using superconducting qubits. Some are using trapped ions, and some are trying to do topological quantum computing with Majorana qubits. There's also a number of breakthroughs in the academic sector here. I'm just listing one that I'm aware of most recently from Misha Lukin's group, where they realized a 256 Rydberg atom quantum simulator, which is a rather remarkable result in my opinion. And so whether or not these companies ever do build a quantum computer, from my perspective, I don't think it's that big of a deal. I mean, I understand they're trying to make money, but from our perspective, we're trying to do science. And I do think this is a great thing for science. And I think there's gonna be a lot of information and insight in quantum dynamics and quantum systems just from these efforts, okay? So I'm not trying to ride the hype. I'm just trying to point out that I think it's an exciting time to think about these systems. And this competition has really driven the creation of a number of noisy intermediate scale quantum devices. These consist of a chain of qubits or an array of qubits. It could be, for example, 2D, like Google's experiment. And these can be run for a finite amount of time or a finite depth of the circuit before it becomes too noisy to continue the quantum computation. And so if we ever want to learn something about this quantum system as it's evolving, we're going to have to measure it. But to measure something, we now have to couple our quantum mechanical system, which so far have been remaining isolated. I now need to couple this to an environment, our measurement apparatus. And then this is going to be something known as an open quantum system. with dynamics that's a bit different than conventional unitary dynamics. Okay. And as was discussed in the formulation of quantum mechanics in great detail, what is the role of measurement on the wave function? And this is something I think should be taught in much more depth, but what was come out of all these discussions and what we all understand now from quantum mechanics is that if I make a measurement, I have to update my state. So my wave function is updated based on the measurement projection and a renormalization. So if it's a global measurement, this is going to collapse the state. But what about a local measurement? Okay, so this process is true for any measurement. And I would like to just give you a simple example to contrast global versus local measurements, just give you some intuition. So let me just start from 3 spin halves, and I'm going to write down a very generic many-body state, complex coefficients, and the so-called computational basis of up and down of these qubits. So let's do a global measurement. Let's say I measure up, up, down. So then my state has been collapsed to up, up, down, and it's normalized. What if I measure the second spin and I measure it to be up? Okay, so now I have to project and then renormalize. But the key takeaway from the local measurement is that you still have a superposition over all sites that you did not measure. Okay, so though you collapsed part of the wave function through measurement, you did not collapse the entire wave function. And the fact that the superposition survives remains that this remains entangled even though you have made a measurement. Okay, this is a very important point. And now if I hit this state with a unitary operator, unitary time evolution, I should be able to then re-entangle this projected up spin with the rest of the spins, producing again an entangled state of all 3 spins. Okay, all right, so this is a very important point before we go on to n spins. If there's any questions on this, I'm happy to stop here. All right, so this brings us to really a main question of this talk, and that's really, is the entangling unitary dynamics that we're familiar with in closed quantum systems stable to a small but non-zero local measurement rate? Okay, and this actually I found a rather profound result. The answer is yes. Okay, this has now been basically rigorously established in a number of cases, and as a result of the fact that this is stable, it implies there must be a phase transition between a highly entangled volume law state to a weakly entangled area law state. And this phase transition is going to occur the dynamics of the entanglement. So it's going to be a highly unusual phase transition, one in which we have really not encountered before. Okay. So how does this relate also to quantum computing beyond just learning properties of the system? So one could think of this open quantum system, instead of being measured, you can imagine, well, my gates have a small but finite error rate, eta. Okay. And it was argued in this rather beautiful paper was that if that error rate is sufficiently small, you actually have a quantum coherent evolution, and you can still do the quantum computation. But if that error rate is too big, the computation becomes purely classical. And there's a phase transition in the ability to do the quantum computation. And Dorit argued this should be a percolation-like transition in the entanglement structure. And now I'm going to go on to classify that phase transition in well-defined microscopic models, because this is a rather, I think, insightful and inspiring work, but hard to make concrete calculations from it. Okay, so that's the first section of the talk. This is going to bring us now to the measurement-induced transition. So we want to construct the simplest possible models with really no other structure that's necessary. So we don't want any conservation laws or anything like that between entangling gates and collapsing the state with measurements. So let's take a cue from quantum information, and we're going to use these so-called random quantum circuits. If these make you uncomfortable, they shouldn't. Okay. This is actually what Google is realizing in their quantum computer. They're just realizing Haar random gates, and they're running it over a finite amount of time. So it's literally the model we're trying to simulate. So I'm going to focus on 1D. So this is a 1D chain of qubits, starting from some trivial classical state, and we run it as a function of time. And each blue square represents a 2-qubit gate, ui I plus 1. So I'm going to have 3 different types of qubit gates in this talk. So the first one, which I'm going to call the most generic quantum gate, which is basically a random U4 matrix, which is the most generic quantum gate one could find. And we're going to be sampling these gates from a Haar distribution. That is, the eigenvalues of this matrix live on the circle. And this is going to be a highly entangling gate. So this is the most quantum kind of gate we can have. We can take a semi-classical limit where we replace the local Hilbert space of 2 to be Q, and we take this local Hilbert space to infinity. Okay, this is kind of like an SUN. This is a UN or UQ as Q goes to infinity. And this is an analytically tractable limit that we're going to discuss. And there's also a numerically tractable limit where these are taken from the Clifford group. And these are known as stabilizer circuits. And these can be proven to be simulated with classical efficiency. But in the back of your mind, you should always be wondering, is this truly quantum? And I'm going to be arguing this is actually just another non-trivial semi-classical limit, because these map a Pauli string, which is a product of Pauli operators, to another Pauli string. It does not produce superpositions of Pauli strings. Okay, and I'll come back to that point. Okay, so now we have our unitary gates, and now we want to intersperse measurements into this model. So I'm going to not measure every site because that would collapse the state. So I'm going to come in, every green dot means I flipped a coin, and I'm going to measure with some probability P. Okay, so let's say I flipped all the coins, and these are the places I'm going to measure with the red X's. Okay, I hope that's clear. The green dots does not mean I measured, it means I attempted a measurement. I flipped a coin. Once you make a measurement, the unitary dynamics is no longer unitary, and it's highly non-trivial because it's a nonlinear effect on the state. Okay, so in between these unitary operators, we now have projection operators. There used to be one projector onto whatever I measured up or down, or identity operators. These are known as Krauss operators. These Krauss operators I could have sandwiched together with my unitaries, but just for visual clarity, I'm going to separate them for here. And after you project with a measurement operator, you have to renormalize the state. So it's a nonlinear effect on the state. Yes? Every blue box is a different random unitary. Yes. For this model I'm talking about, we sample a distribution of matrices. It's a good question whether that's an essential piece of ingredient, but yeah, let's not get into that. Okay, but
the projection is local also?
Definitely. So the projection, this would be a projection onto that site. And if I measured it to be up, just to measure with Born probability. So if I measured it to be up, that'd be a projection onto up.
At that measurement, do you lose phase information of the projected object to everything else or locally?
Well, you disentangle that one site from everybody because you've projected it to be up. So I think you lose the phase information to everybody. I think that's.
Let's say I have this object.
Yes.
Place I, which you are measuring,
Mm-hmm.
and it has some specific phases with respect to all n objects. Are you putting all those phases to a fixed value after measurement?
Oh, so I actually had that in the example. So Chandra is asking, what is the action of the measurement on the state? Let me just go back to that, because otherwise I can write it on the chalkboard, but then nobody's going to see it. Yeah, right here. So this is the action of the projector. Okay. Oh, where my laser pointer go?
You can only give one of two answers.
Yeah, you only have one or two answers, up or down. And if I measured up, I had a Born probability, which led me to select up, but I still have this complex coefficient, but it's fixed that index to be up. So that should answer your question. I may be not understanding precisely how you're asking the question, but so there's still phase information. I mean, this is a complex coefficient, but you fixed part of them. You erased a lot of them, right? Anyone that has a down there is gone, projected out. Okay. Here we are. So the other point that's very important here, so the projection and renormalization is nonlinear, but now your wave function has a time and it depends on the measurement history, okay? Which means if I compute any expectation value, it's going to depend on the trajectory of all past measurements. And so to get a physical observable, I'm going to have to average over these quantum trajectories or measurement outcomes to get the final result. And this will have a profound effect on correlation functions. Okay, So now I have one parameter in this model. It's just P. Okay. If P is 0, I convinced you that this is just unitary time evolution. It should be highly entangled. If P is 1, I measure every site. And so I collapse the wave function entirely. And just rephrasing the question I asked earlier in another way, in terms of the entanglement entropy, you can state it as, does this volume law phase survive a finite P? It could be that infinitesimal measurement rate destroyed this volume law entangled state. That's a possibility. But actually, rather remarkably, that's not the answer. And the answer is the volume law phase is stable. So even though you're extracting information from the system, it's able to efficiently hide it back through unitary time evolution, and the volume law phase is stable. So quantum information is, people are very interested in this as an interesting non-trivial quantum error correcting code. And as a result, you have a phase transition as a function of the measurement rate between a volume law and area law entangled state. And characterizing this phase transition is what I'm going to be spending the rest of the talk on. Okay. So let's discuss the large Q limit. The large Q limit is intimately connected to the zeroth Renyi entropy, but this is a little too technical for that audience. So let's stick with this large Q limit. So we have Q dits, very large Hilbert space, and we take Q to infinity. So in this work, what that was shown is that if you define a replicated field theory to compute this Renyi entropy, so you have a replica from the random gates and you have a replica from the Renyi index, you can actually map this problem to a bond percolation problem in one higher dimension, where that higher dimension comes from the dynamics. Okay, so we're mapping. So so this circuit has no measurements. We did no measurements. So this gets mapped to a network in space-time, and the entanglement is characterized by the number of bonds you have to cut in this network. So this is a volume law entangled state. Now I introduce these measurements, same places I had before, and this should be 1-to-1. And so now I start coming in with measurements. I start cutting apart my network. Okay, so measurements cut the network apart. And so then you can start understanding why I'm saying bond percolation, because I can view these two phases now as a connected network where the measurements were not enough to disconnect it. And I can still percolate through the network. So I have a volume law entanglement, or the measurements were too strong, almost like a Zeno effect, cutting across all these bonds, producing a constant entanglement entropy.
That's a classical percolation problem.
This is a classical percolation. This is percolation. So in the replicated field theory, it maps to a Q factorial state Potts model, random bond, which was Q goes to 1, it gives you percolation. Okay, yeah. And classical limits of this problem is also interesting. I'm happy to talk about that. But this is not. This is a semi-classical limit. So there's still some quantum mechanics in here. Like you do SUN, I'm sure you don't like to get rid of all the quantum mechanics. So at the transition then, this predicts this should be in the bond percolation universality class. So I've borrowed a rather beautiful picture at the critical point of bond percolation. And you can see this is basically a fractal network. And this gives rise to a logarithmic scaling of the entanglement entropy. And if I can now characterize the critical properties, they're just known. Let me just tell them to you. So you have a correlation length, which is isotropic in space and time, which you have a dynamic exponent Z is 1. You have an emergent Lorentz invariance at this critical point, and you have an exact statement that nu should be 4/3. Also, correlation functions in the percolation limit are fractal. Okay, they are not multifractal, and this will be a very important point I come back to at the end of the talk. And the last piece of information I'd like to provide you is that bond percolation critical theory is actually described by something known as a logarithmic conformal field theory. This is an odd beast. It has a central charge C equal to 0. Okay. So let me move on now to the controlled limit of numerics. These are using the Clifford stabilizer circuits or Clifford gates. And as I mentioned earlier, it's a very important point. You should not be hoodwinked by Cliffords. They always map a polystring to a polystring. They never produce a superposition of polystrings. So this is not a generic quantum gate, and there's not as much quantum dynamics as there would be by taking something like a Haar random gate. But this allows you to do really big system size simulations. For example, done by Lee, Chen, and Fisher, all the way up to 500 qubits. And you can see for weak measurement rates, so these are P's. So this is low measurement rate. You have a clear volume law entangled state. At large measurement rate, you have an area law. And at the critical point, they do indeed see a logarithmic scaling of the entanglement entropy. But the coefficient, which is a universal predicted value from percolation to be 0.55, is far too big. Okay, so there's one indication that maybe the Clifford CFT is not the same as the bond percolation CFT. You can also then try to do data collapse. So if you do data collapse for a living, this should give you nightmares, as it did to me. It's a lot of assumptions, a lot of fit parameters, and you can see the collapse, it works, and it gives a nu, which is close to percolation. Oh, there's a couple chats. Okay, so here we are. So Greg Moore has a question. When you speak of phase transition, is it implicit that some kind of thermodynamic limit is being taken? Yes, we are taking thermodynamic limit in space and time. I don't know where Greg is. Maybe outside Flug. Okay. And then Matt Foster responded to Greg, to the extent that the ultimate transitions are apparently log CFT similar to classical 2D percolation, I would assume yes. So we just said the same thing. Okay, Greg, please let us know if you have more questions. All right. Great. So where was I? Clifford. Yes. So based on this, at this point in time, it was really not obvious how you extract the critical exponents and even critical point in an unbiased fashion, right? So we want to find something where you don't have to use any assumption about criticality to locate PC and to estimate nu. And if we're going to do Haar random circuits where we can't get to 500 spins, this is going to be an essential thing to do. But before I go on to our work, let me just mention some other interesting extensions. So when I started out, I said, if random quantum circuits make you uncomfortable, you should feel better now because I can replace them just with the unitary time evolution of a many-body Hamiltonian, which is not many-body localized, and my gate would then be this unitary evolution over some finite amount of time delta t. Yes?
Unitary evolution with local.
You don't have to have a local Hamiltonian, as I'll get to here. But that's a very good distinction. So to distinguish between area law, volume law, it does need to be a local Hamiltonian. But if I introduce, so let me just get to your question. Very good question. So you could also relax these projective measurements to weak measurements. It still survives. You can actually get rid of all the unitary dynamics altogether and select only projective dynamics, but the projectors have to not commute. And you can also drive a similar transition in that way. And to come to Gil's question, if you have long range interactions, the volume law and area law phase will no longer be distinguished because even if I have a collection of long range Bell pairs, which is trivial, it'd still be volume law. And so the way you can distinguish this is actually starting your initial state from a mixed density matrix and asking, does my non-unitary evolution purify my mixed density matrix? Does it remain mixed? And this was by Gollins and Hughes, where you can actually show that this transition survives as a purification transition. So locally, it's the same, but if you have long range gates, you have to use such a purification language. Thank you. Yeah. I should specify my Hamiltonian is local in the future. Okay, so just before I go on to our work, we're running out of time. So this is something that people seem to not point out when they give these talks, but I think it's actually an essential part to understand the physics. So this is an unusual phase transition as it takes place in the quantum information. And simple correlation functions, average over measurement outcomes, are insensitive to this transition. And there's a very nice argument from Skinner, Ruman, and Nahum on this. And in my group and people at CCQ, we've been thinking a great deal about maybe how to prove this or how to understand this more deeply. So let's just understand the argument. So the argument is as follows. So let me compute a correlation function, depends on my measurement history. So then I average this over my measurement outcomes. Okay, this looks like good old correlation function. I have a critical point. It should see the transition. But I can actually rewrite C of xy as a trace over a completely mixed density matrix, mixed over all possible measurement outcomes. As time goes on, this is just the infinite temperature Gibbs ensemble for any measurement rate and will be completely insensitive to P. So these correlators simply averaged over measurement outcomes will not feel the phase transition. But you can construct objects that do by forming nonlinear averages over the measurement outcomes. This object is sensitive. And everything I've told you so far, entanglement is a nonlinear operation in the reduced density matrix conditional on measurement outcomes. So everything I've told you so far satisfies this condition. Okay, I do think there will be some proofs beyond these arguments coming out soon. Okay, so let me just summarize everything I've told you about this so far. So I've given you two controlled limits, large on-site Hilbert space dimension, and stabilizer circuits. So an analytic control, numerical control, they both yield a Lorentz invariant transition, seems to be consistent with percolation, though the stabilizer circuits, there are some differences that remain. And the transition persists in a number of different model settings. It also persists in higher dimensions. And this then brings us to our work. What if we take fully quantum Haar random gates? Can we find a universality class which is fundamentally beyond percolation? Okay. Yes.
The object you just showed, the transition, it kind of looks like a variance.
It's like a connected correlator that you average over measurement outcomes. So yeah, it's like a variance over measurement outcomes. So there's definitely, yes. So the distribution of these objects over measurement outcomes, as I'll get to, is a rich thing to look at. I won't look at correlators. I'll look at something else a little more exotic. But yeah, probably related actually. Okay, so the remaining time, let me tell you about our contribution to this problem. Just to restate the question over and over so it's clear, does this fully quantum problem with generic quantum gates belong to a different universality class? Okay. And again, the scaling on SOTs of my nightmares needs to not be used. There's far too many assumptions. So we wanted something like a Binder cumulant, if you're familiar with magnetization, which would cross at a critical point and be just a way to detect a transition without any assumption of the problem. So we borrowed insight from the tripartite mutual information, also known as topological mutual information, which was used to calculate the correction to the area law in 2D topological quantum field theories by Kitaev and Prescott and Levin and Wen. And the hope was that this is our system, periodic boundary conditions, and we divide it into 4 subsections. And the hope was that if our insight is correct, this should cancel the log L criticality in this object, and the data should cross at the critical point. And indeed, when you do this calculation up to 24 qubits, you can see a rather clear crossing in Haar random circuits. And the beauty of having Clifford circuits around is you can do the same calculation on small systems, get a PC, which is quite close to the value you get on 500 qubits. So you can know in the Clifford case, there was no large finite size drifts, basically eliminating a good estimate of PC. So I can't prove that's true for Haar, but it does give some motivation that it's probably a pretty good metric. And we actually have a couple other metrics I won't mention, but they all give consistent estimates of PC in an unbiased fashion. You can now collapse the data with minimal assumptions. And here's the Clifford value, which we kind of already saw. But lo and behold, that Haar value is unfortunately quite close to percolation. Okay. So we haven't found anything different. So we can also introduce the notion of a local order parameter. So if we have our quantum system running and I'm an observer, I have an ancilla qubit, I have my own little qubit, and I couple it in at some space-time point, and I'm going to track the entanglement of this qubit. So I'm going to trace out everything else, okay? And the intuition is that the order parameter should just be the entanglement of this ancilla qubit, because my system is highly entangled and I entangle the ancilla qubit, that locality will be lost. It'll be highly entangled with everybody. It'll remain non-zero. Whereas if I couple it to an area law entangled state, it'll go to 0. And indeed, these are just the words I just said out loud. Indeed, if P is less than the critical value, this remains entangled, non-zero value, whereas if it's past the transition, it vanishes in exponentially fast fashion. This order parameter is very nice because at the transition, you can use this to determine the dynamic exponent of the transition. And indeed, we find a Lorentz invariant Z equal to 1. Okay, so we found a new close to percolation. We found Z close to 1. So everything so far seems consistent with the percolation results so far. We want to get more critical data. So we can now compute a correlation function in this critical theory. How do you do that from the quantum circuit? Well, you now entangle 2 ancilla qubits at 2 different points in space. We'll do the same point in time, T0. And the argument would be that the mutual information of these 2 ancilla qubits will map to a correlation function in the critical theory. So if that ansatz is true, then this should have a power law decay as a function of separation of my ancilla qubits. And I can now test this ansatz at the critical point. And indeed, I see very good data collapse. The inset shows the uncollapsed results. But yet again, eta is incredibly close to percolation. Okay, so borrowing this insights from Clifford's, we can look at the entanglement scaling at the transition. Again, we do see this log L scaling, but the coefficient is a non-trivial function of the Renyi index. We can actually get this reasonably accurately shown here. And this is actually alpha of n is known for conventional CFTs rigorously to be 1 + 1 over n. Okay, so the fact that this is not 1 implies this is not a conventional unitary conformal field theory. So we're already seeing this is a very strong indication this is something beyond that. But I was left at the end of this project rather dissatisfied because we cannot discern with the numerical accuracy we have between these three universality classes. PC is not a universal number, this should not agree, but nu and eta should be distinct. But critical exponents being close is quite common. Consider the Ising model, the Heisenberg model, the XY model on 3D. Nu is very close to each other. It takes very good numerics to tell them apart. And so we were kind of left all arguing with each other at the end of this paper, is Haar random circuits simply percolation? And so I never thought it was. And so luckily, as I will try to convince you of it is not, actually I will have strong evidence it's not. And so with the last bit of time, we're going to directly characterize this logarithmic conformal field theory at the transition. So I don't have time to get into like all the insights we used to get here, but let's just, what we did is we borrowed a number of insights and intuition from these replicated field theories in the classical limit and the machinery they use, and we translated it to the quantum problem. So the field theory of this percolation transition, let me just remind you, is this logarithmic conformal field theory. So why I got that name, CFTs have power law correlations. There's multiplicative logarithmic corrections to that, hence the name log CFT. Sorry. And as I've pointed out, it's rather unusual. It has 0 central charge. So this equation is really just for the experts. You don't have to dwell on it. But the way it's defined, so the way the effective central charge is defined is as follows. So if you have a replica field theory with a replica index R, the central charge is a well-defined discrete number, 1.5, whatever the problem is. And then the effective central charge, which characterizes these logarithmic conformal field theories, is the rate of change of this object as the replica index goes to 0. Okay, so it's a weird object, but we can compute this in the circuit, as I'll show you. So the key insight from our recent work actually is that the logarithmic conformal field theory can be characterized via a non-unitary transfer matrix. Okay. And for the rest of this talk, I'm only sitting at PC, so I'm not varying P anymore. I'm just sitting at the transition. In conformal field theories, it's very natural to work with really long cylinders where this dimension is infinite, and then the circumference is small. So you can get finite size corrections in the circumference, which have universal properties. Okay, so rewriting our dynamics, our non-unitary dynamics, we can identify a transfer matrix, which we label here, which is an entangled unit, and we can just rewrite our time evolution as a very large product of transfer matrices. And so if I have transfer matrices, I usually analyze the eigenvalues, but I have random transfer matrices, so I need the Lyapunov exponents. Okay, to get to there, we can compute the singular values of this large product of transfer matrices, which decay exponentially with exponents that are dependent on the measurement history. Averaging these over the measurement history, we obtain the Lyapunov exponents of the random transfer matrix. And these Lyapunov exponents have a great deal of physical insight to them. So the leading Lyapunov exponent is actually related to the free energy of the conformal field theory. And there's a number of steps to show that that free energy we can compute in the circuit model from the probability, from the Born probabilities of that measurement trajectory. So it's actually a rather beautiful result because this is the Shannon entropy of the measurement record. It's showing you that the information is physical and it's actually the free energy of this conformal field theory. We can also compute logs of correlation functions in the CFT by looking at differences of higher exponents. So this J would be like 1, 2, 3, and 4. In practice, numerically, we can only compute a few of these because these are giant matrices, and I'm happy to talk offline how this is actually done. But this is a statement that these differences allow us to probe the correlation functions of the order parameter of the CFT. So going to higher J, you get a very complicated combination of operators, and it may be quite hard to understand what actual correlation function you're measuring. But the first few ones we can understand. Okay, so here's our free energy density, and conformal field theory predicts that there's going to be a correction from our finite size circumference, and that coefficient is precisely this effective central charge. Okay. And what I need now, I need to compute the free energy. And this actually just I get for free just by running my non-unitary dynamics. Is that a question? Okay. And I now need to compute the area of the cylinder of the CFT, which is implicitly defined. So I don't know alpha a priori. It's a property of the system. But we can be clever. So in the paper, we computed alpha directly, but we can be more clever than that. And we're collaborating with Sarong, so he's a very clever individual. And what you can do is actually, is you can take something called dual unitary gates. So these are still within the Haar random universality class, but they're unitary in space and time. So even in the presence of a measurement rate, you can graphically prove alpha is 1. Okay, so this eliminates any error from the computation of alpha, and we only have error in F. So this is the most accurate estimate we can provide. But if you look at the paper, we have a separate estimate where we computed alpha from the CFT for a slightly different set of gates. So here's the free energy density versus 1 over L squared. And you can see a rather clear linear relationship, which allows us to estimate the effective central charge. If we now take the Q to infinity limit, this was computed by Roman and Andreas, and they get a value rather distinct from our numerical estimate. So indeed, this is not the same CFT as bond percolation. We can do the same thing for Clifford's, and we again get another value which is distinct from all three and well outside all the error bars. And so indeed, we've identified 3 distinct log CFTs. So there's something subtle with the Clifford's, where if you take the infinite dimensional limit of a Clifford gate, you need to work harder to really show this is distinct from the infinite dimensional limit. I'm happy to talk about that offline, but the conclusion is here. These are 3 distinct log CFTs. Okay, so numbers are nice, but it'd be better if we had a physical piece of information that's fundamentally distinct. Yes?
Very quick question. You know anything about nu?
Yeah. So nu. So when we so computing nu from the transfer matrix. Do you mean? So nu is very So I showed you nu earlier, and it's you can't tell the difference between percolation. Computing nu from the transfer matrix, we haven't figured out how to do that because you have to define an energy operator in the quantum circuit. But I don't present it. But we computed eta with the transfer matrix because that is directly part of it, and you get a much more accurate estimate than we had before, which shows it's distinct from percolation. So the nu we don't have accurate enough, I would say. Yeah. Well, we don't have the CFT. We're just computing properties of this transfer matrix that reflect CFT. The CFTs, in these large these limits, like large on-site Hilbert space dimension. You see what I mean? No. Yeah, that's known. That's exactly that's this number. Okay. And nu is 4/3. It's exactly known. Yeah. That's what I was always comparing against. Okay. But I'm going to finish in a second. It would be much better if we could actually identify a physical consequence of quantum fluctuations in this Haar random circuit, which is like a phenomenon beyond Clifford's or percolation. And indeed, we have done that. So going back to this correlation function in the CFT, if I take percolation or Clifford, if I take an average of this correlator, it's in a decay with a universal exponent xj. And this is something that's it's fractal, but not multifractal. What does that mean? So if I now raise this correlator to a power n and do the average, n appears in a trivial multiplicative factor times xj. So this is just a fractal correlator. So what I'm going to show you is that is a consequence of these semi-classical limits in the fully quantum mechanical problem. This becomes a multifractal log CFT. And how do we show that? So now if I take this correlator to the power n and then average, the question is this exponent a nonlinear function of n? If it's a nonlinear function of n, that implies every power of n has a distinct critical exponent. And that's what multifracticality means. Okay? So we can actually compute x1 of n to the first 2 powers using a cumulant expansion of log g, because log g is self-averaging. We can average log g nicely. And from the cumulants and CFT properties, we can compute these universal exponents. Okay? And doing so, you do again see this 1 over L squared scaling, but it's rather remarkable that this is so big. It's actually larger than x1, 1. So this is indeed highly multifractal. And this was properties, these are moments of the distribution. What about the distribution of correlation functions? So based on Andreas Ludwig's previous work, the scaling ansatz for a universal multi-scaling function, h, which is unknown, should satisfy this property where y is our log g, which is the difference of these first two Lyapunov exponents. And we can then collapse our data in this distribution. So this is h of s. So as you go to larger system sizes, larger times, you get one unique function, and the minimum appears precisely at x11 of 0.122. Okay, so this is indicative of a multifractal distribution. And so indeed, the Haar random universality class is fundamentally distinct from the large Q limit or the Clifford case. So just to conclude, I hope I've convinced you that this is a transition, this novel dynamical transition. It occurs in the structure of the entanglement. We provided unbiased accurate estimates at the critical point. And this transition is described by log CFTs. We computed the effective central charge. And I showed you that keeping the complete quantum nature of the gates uses a multifractal log CFT that's fundamentally beyond percolation. Just before I conclude, I'd like to point out that log CFTs with multifractal correlations, as was brought to my attention by Matthew Foster, are rather unusual. And these have actually been seen in his group on the surface of topological superconductors with disorder and interactions. So surprisingly, I'm able to bring back the universality class to the workshop that we've been discussing so far of topology and interactions. Surprisingly, universality can connect these two things. So thank you for your attention.
There are a couple of comments that just came into the chat.
All right.
We might start by reading those.
All right, so here we are. In addition to Clifford circuits, there are a class of circuits called near Clifford circuits, where one has small angular rotations or a small number of non-Clifford elements. These circuits can also be simulated efficiently with a stochastic element to them. As one adds in the number of these non-Clifford elements, it seems like there may be similar dynamical transitions between these two different log CFTs. Thoughts? It's a very nice question. So we actually tried initially to look at the Clifford fixed point and perturb it with like a small finite density of Haar gates. So your suggestion is, I think, a bit more controlled. It's a very nice idea, and I'd be happy to try that. But what we found, it was very hard to see the flow of the fixed point. So since C is equal to 0, there is no C theorem to guide you on relevance or irrelevance of operators at a fixed point. So it's a very nice question, and yeah, I think that should be looked into. Okay, so Matt asked, do the multifractal exponents correspond to those of the spin quantum Hall effect, which shares a few exponents of percolation? The anomalous most relevant operators go as 1/8 Q times Q minus 3. Oops, he had a typo. Also, there's now a claim that spin quantum Hall plateau might even exhibit local conformal invariance. Hey, Matt, can you maybe clarify your question?
Can you hear me?
Yeah, I can hear you, but I'll just repeat your question to the audience.
Sure. Okay. So the question is the multifractality that you measure, right? So spin quantum Hall is like it's a different version of the integer quantum Hall plateau transition, non-interacting. It's purely quantum wave interference in disorder in some funny Altland-Zernbauer class. But Ilya Grusberg and Nick Reed and company showed that some of the exponents are exactly the same as percolation. And moreover, you can compute numerically all of the multifractal exponents for the most relevant operators, and they have this, they're almost parabolic, and it's given by this spectrum
these are typical exponents?
These are typical exponents.
Yeah, so we did compute, so with the transfer matrix, to answer your question, we did compute, I didn't mention it in the talk because it was a little too technical, we did compute the next relevant operators. And with the transfer matrix approach being much more efficient than data collapse, we actually were able to show that, for example, eta, the order parameter exponent, is distinct from percolation. So we do know eta is at least different.
I see, but this multifractal spectrum you mentioned, does it?
That's we didn't look at it beyond those two numbers I quoted and
Okay,
H of S. So that's a very good. We can look into this into more detail.
So the one other thing I just wanted to mention is that this recent work by Ilya and Jonas Karcher and Sasha Merlin, so they're trying to figure out spin quantum Hall, and they are making a very big claim, which is that maybe spin quantum Hall doesn't even exhibit local conformal invariance, which if it were true, doing things on a cylinder might be different than the plane. So it's just something to keep in mind. So, I don't know.
Did everybody hear him? I don't even think I could repeat that. Okay, thank you, Matt, for that comment.
Okay, sorry.
No, yeah, I don't know what to say about that. I mean, with us, we can't, the cylinder, we're really restricted to this. I mean, the geometry of these simulations, you can't really do big squares, right? So, okay, any questions? Yes.
So the measurement you performed in each case, it's always the projective.
Fully projective.
Which,
Sorry, she's yes, you're asking if the measurements we're performing always fully projective. Yeah, stating. Sorry. Okay. Yes.
So how would things be different, or do you have any idea what happens if
You mid-week, like a weak measurement. Yeah. So there was work I mentioned. Okay, to repeat the question, what happens to the transition in the presence of a weak measurement? So let me just credit the people who did this work and just get to that slide. Sorry. So the answer is it remains, and you actually get an interesting phase diagram that I will sketch. So I mentioned these extensions very briefly, so I should have spent a little more time on them. Okay, so in this work here, that was exactly the question that they asked. And so if you have a probability to measure, let's put that on the x-axis, and you have a strength of measurement lambda, you get a phase diagram. You get a phase diagram like this. This is volume law, area law, and the numerics were kind of, earlier on. It was before a lot of these unbiased methods were developed, but whether the universality class is the same, maybe that's one of your questions along this line. It seemed to be yes, but I think that question should be, I don't think it's closed. It's definitely an open question, I think. Yeah. Okay. Any other questions? Yes.
Yeah, I have a lot more basic questions. So this differentiation between volume and area law entanglement.
Yeah.
Does that also differentiate between a quantum computer that is useful for doing quantum computations and not? Precisely.
So that, let me just.
Question.
Oh, sorry. So to rephrase Cyrus, I got too excited. Sorry. To rephrase Cyrus's question, does this volume law to area law entanglement have something to do with being able to do the quantum computation or not? And that's precisely what this work argued here. So what was argued or shown was that if you are still volume law like entangled, you can still do the quantum computation. But if you lose that entanglement, you become area law entangled, even short range entanglement, you'll still only be doing a classical computation.
It's really a sharp cutoff.
It's a phase transition, yes, in the amount of information you can process in some sense. Yeah, like the Hilbert space is so big, right? Okay. Yes.
You know the position of the critical point with some finite precision.
Yes.
So is it possible that because you're a little bit off the critical point numerically, the exponents are also a little bit off from?
Well, that's what error bars are for. Sorry. Oh, the question is the inaccuracy of PC leading to your inaccuracy of exponents, and I mean certainly in some aspect, and we have error bars, and the error bars are not small, and that's why we can't tell the difference with these data collapse methods. So this transfer matrix approach also, I didn't get into this, but this effective central charge is maximized at the transition, and you can add another metric which gives this estimate we gave even more accurate, and yeah, so in that case, we're able to really pinpoint this exponent eta to higher accuracy. But nu is still not, we still haven't gotten nu very well. I think Piers was next.
Yes, don't forget to repeat my question. Can the current generation of noisy quantum computers test this?
The answer is yes. So the question is, can this generation of noisy quantum computers test this? And Chris Monroe's group has demonstrated both of these phases in a trapped ion quantum computer. So yes.
And the transition?
There's 6 spins. So I mean, that's I think one, yes, eventually, but in the first.
But with the current generation of quantum computers, can it be tested?
So with the current trapped ion simulator, it was tested and 2 phases were found. And now to really demonstrate the critical point, you'd have to get to more spins. And Misha Lukin's group, demonstrating this very large simulator, can't measure as it's running. So, I don't know if they'll be able to get to the transition yet. In the Chris Monroe experiment, they did some tricks to deal with the measurements. They kind of like did them in a way where it didn't destroy the revolution. And so getting to the critical point, I think, is going to be a major challenge. But the area law phase driven by measurements was observed. Yes. I think Richard and then Gabe next. Yes.
Is there a sense in which from SU4 you could get rid of the generators and then just keep left with the cotton generators, and then that will be equivalent to the Clifford algebra?
So can you say it again?
Is there a sense that you could interpolate between these 2 different universality classes by getting rid of the generators of the SU4?
Okay, so Yashar is asking, can we flow or interpolate between the Clifford fixed point and this Haar fixed point? And that was related to a question that was asked in the chat. And I mean, conceptually, I do think the answer is yes. So you can define Clifford gate with a small mixture of Haar or something like this, and you could see if a fixed point flows to another fixed point. And as I mentioned, there's no C theorem here. So how it flows is unknown. But I think that's a very nice, interesting question that we tried to explore, but we didn't get very far, but that doesn't mean much. There's probably a lot there. Yes, Gabe?
Because my question is related to Pierce's question, primitive question. So how long did it take to do these simulations classically versus how long did it take Chris Monroe?
So Chris Monroe, so the question was, I don't know how long it took to do his actual. Okay, so Gabe's question was, how long did it take us to do the classical simulations versus the quantum simulation? And I do not know how long it took Chris Monroe's system to run. It probably didn't take very long, but it did require a lot of statistics. Yeah, but the thing is the classical simulations also require a lot of statistics because you're sampling. Not only are you trying to do quantum mechanical averages, you're sampling this trajectory space. The trajectory space is incredibly rich. So you have, I think it took us a lot longer, is my guess.
So the point is that if you run this,
but we had 24 qubits and they had 6.
but of course yours were run on a classical machine.
Right. If I did 6 qubits, I could probably do it comparably.
What kind of classical machine was this?
Oh, these are just good old supercomputers. Nothing fancy. We just use Amarel, the cluster at Rutgers, and just go to town. And if you want to go to bigger sizes, you could use large memory nodes. We didn't even have to do something like that. So this is not like diagonalizing a many-body Hamiltonian, which is very expensive. You have a state vector and you have a unitary gate, which is very sparse, right? It's a 4x4 matrix in this giant Hilbert space, and you have to put it out there. So it's all sparse matrix vector operation. So what we use was that technique. And to get to the transfer matrix, obviously, we never built one of those actual transfer matrices on the computer for 24 or 20 spins, right? That would be impossible. We did build it for a small number of spins and then check that you can compute those Lyapunov exponents almost in like a Ritz vector or Langstos kind of method using like mutually orthogonal vectors. I can talk about it a bit more. But in that case, we could only get like 3 of those vectors. So 3 of these Lyapunov exponents we could get accurately. And the non-unitarity actually starts to kill the norm of your vectors because you're projected, right? So that projection kills the norm, and so you can't get all the Lyapunov spectrum unless you have more power than we have.
Any more questions?
Jed, there's a question from Chris.
Oh, okay. So thank you, Matt. I don't see the chat. Chris, can you ask your question?
Sure. I just wanted to ask, is there a solid argument that there are only two fixed points here, one for the Cliffords and one for the Haars, or might there be more?
So that's a very nice question. In the current case, so that's Chris Hooley, right, Chris? I don't see your, yes, all right, hi, Chris. So his question was, could there be more fixed points than just Clifford or Haar? Or do you mean within one model there could be more fixed points? Chris?
Yeah, so like within this kind of random circuit thing, but with some different statement about the distribution of the gates you
Right.
use. How do I know there's not a third one there somewhere?
Very good. You don't. So I can tell you we have some recent work in the presence of a conservation law, and you can actually identify another phase where you purify in the conserved quantity, but you remain volume law entangled. So introducing conservation laws, for example, is a very rich direction. And that transition is a different universality class than all of these. So to answer your question is yes, I think if you play with your dynamics, you should be able to find different fixed points. But my intuition would be that in some limit where it's basically full enough in the quantum dynamics or quantum scrambling in the unitary, it probably will flow to the Haar critical point.
Thanks.
That's intuition, though. I don't have a strong statement. Okay.
More questions in the chat. So
Great.
we're gonna thank Jen for really good talk. The live participants can prepare to the patio for.
Hey, Chris. Hey, Matt. Good to see you guys.
Pleasure to see you. Thanks for a nice talk.
Thank you. Thanks for tuning
Jen.
in. Yeah, thanks, Matt. We should catch up on this stuff.
Absolutely.
Great. Okay. Good to see you guys. I'm gonna log off.